Now that we've kind of discussed the basics of electromagnetic radiation, kind of laid a foundation for it, the next thing we want to talk about is the actual speed of electromagnetic radiation. And as you're aware, it's quite fast. It's that 3.00 times 10 to the 8 meters per second. So when Hertz had done his little experiment with the radio antenna and such, he was able to show that the radiation traveled at about 3 times 10 to the 8 meters per second, and empirically verified sort of Maxwell's theories. Now that was good, but we want to put a little bit more concreteness to his measurements. Now, over the course of time, there had been many attempts to determine the speed of light, some good, some not so good. So we're going to look at a few of them today, and then we're going to start to move into the more concrete one. So the first person who really tried to measure the speed of light was Galileo. Now, when I say try, we'll say he made a nice effort. You'll see momentarily his execution was not particularly smart, but we'll give Galileo credit. He at least tried. So Galileo's methodology for determining the speed of light was to use his assistant to help him out. So we're going to do a little sketch here. We're going to have a couple mountains here. So we'll have Galileo's assistant over here. We'll have Galileo here. We'll give him one of those nice two-door bonnets, as was probably the style at the time of Galileo. So, we'll give him a nice little hat here. And anyways, the main thing with this methodology is that these two mountaintops, they're about 1 kilometer apart. Now, what Galileo had wanted to do was he wanted to measure how long it took light to travel this distance and back. So Galileo and his assistants, they both had lanterns shining light, and they were both able to cover up that light. So this was the plan. Galileo was going to uncover his lantern, and the light would shine from his lantern, and it would reach his assistant. When his assistant saw the light, his assistant would uncover his lantern, and the light from that would reach Galileo. What Galileo was going to do is he was going to use a pulse as a referent. He was going to use his pulse to time how long that was going to take. Well, turns out that method doesn't really work. Light takes about 3.34 microseconds to travel 1 kilometer. So using your pulse to time that, not going to work very well. If your pulse could successfully time that, you have some serious problems that you need to worry about. So Galileo made an attempt, not really a great one, so he kind of moved on and did other things. So the first real attempt to get a number were from these gentlemen named Roemer and Huygens. So they devised a better method, and they used one of Jupiter's moons, Io, to help them out with this. So what they were looking at is they were looking at the eclipsing of Io. So they had noticed that when they observe Io, they had noticed that the time it takes for the light from Io to reach Earth depended where the Earth's position was relative to the Sun, which makes sense. Now, there's a point where the Earth is at its closest point to Io. There's another point where Earth is at its farthest point to Io. What they had known is that the time difference between the time it takes from light to go from Io to the shortest distance it is from Earth, to where Io has to take. Let me rephrase that. What they had noticed is that the time it takes for the light to go from Io to Earth at its shortest point and Io to Earth at its longest point, the difference in time was about 22 minutes. So what they had figured out is the time it took to cross this orbital diameter. This time was about 22 minutes. That's something they knew. Now, they would be able to calculate the speed of light if they knew the orbital diameter. At the time, they also had a rough value for that distance across. So they knew a distance, they knew a time. This was going to allow them to actually determine the speed of light. So we can look at that. So based on the figures of the day, Roemer had an approximate value for that orbital diameter being about 2.82 times 10 to the 11 meters. So knowing that distance and knowing that time frame, this allowed Roemer and Huygens to get a rough value for the speed of light. So whenever we're doing speed of light calculations, we're going to use V equals d over t. We're going to use our uniform motion equation because light doesn't accelerate. It's always traveling at the speed of light. So for distance, we have that 2.82 times 10 to the 11 meters. And then for the time, we don't really want to have this in minutes. We'd prefer to have it in seconds, so we're just going to take our 22, multiply it by 60. So we're going to get 1,320 seconds. So that orbital diameter divided by the time it takes to cross that orbital diameter, we get about 2.14 times 10 to the 8 meters per second based on the data of Roemer and Huygens. Now, the value is fairly discrepant. It's about 28% off from the current accepted value, but it was still impressive. It's the first time that scientists actually kind of nailed down a value for the speed of light. Now, you'd think scientists of the day would be pretty proud of Roemer and Huygens. They got a value for the speed of light. Good on them. Let's celebrate. No, it didn't actually work that way. The scientific community thought their result was absurd. They thought it was way too large, and nobody took it seriously. It was only after Roemer and Huygens had died that people actually started to think, oh yeah, light actually does travel pretty fast. Now, they were the first to kind of lay the foundation for this. Eventually, we move into a method that was a little bit more accurate, and this was developed by Armand Fizeau from France. Now, to explain this is really difficult. It'd be much better if I had a video or an animation, so stay tuned. I'll see if I can post that kind of simultaneously with this. But here's kind of the very basic setup of Fizeau's experiment. So he had a light source, and that light source passed through a lens to focus that light, and then it reflected off a mirror, passed through some lenses, hit a mirror that was 8.63 kilometers away. So that distance there is 8.63 kilometers. Light reflected back, and then it was going to be observed. Now, we might ask ourselves, well, how does that help us determine the speed of light? So here's kind of what Fizeau wanted to do. You'll also notice that Fizeau has this little toothed wheel. So here's kind of the side view of it. Here's kind of looking at it head on. And you'll notice that they have these little teeth in these wheels. Now, what Fizeau was able to do is he was able to control the speed of this toothed wheel. So he was able to control how fast it spun. And what Fizeau wanted to do is he wanted to trap the light between this mirror and one of the teeth on this wheel. Because what had happened if he spun the light just fast enough, instead of the light passing through one of these gaps between the teeth, if he spun that wheel at just the right speed, the light would pass through, it'd hit off the mirror, and then it would hit the tooth. What that means is the light would be blocked by the tooth of the wheel, and the observer wouldn't notice any light. So if Fizeau was able to block the light and know the speed of that wheel, he'd be able to get a rough value for the speed of light. And Fizeau did do this, and he got a value of about 3.15 times 10 to the 8 meters per second. Now, we know today that's a little bit high, but he got fairly close. A little bit more work needed to be done, but that will come with time. So he actually did a pretty good job. And we can look at a Feasel calculation. Now, are these the type of calculations you're going to see? Probably not. This is just more to highlight some methodology. So in Fizeau's experiment, so in this example, he's increasing the wheel's frequency to about 12.6 hertz. And he figured that the light, it traveled this 8.63 kilometers and back in a time of 5.51 times 10 to the minus 5 seconds. So we want to determine the speed of light as found by Fizeau. Now, just to really sketch this in a very crude manner, so here's a light source emanating in all directions. I don't know what that's supposed to be. Here's a mirror. Now here's the light. It's going to go to, and it's going to go from. Now it's going to go 8.63 kilometers there, and it's going to go 8.63 kilometers back. Now, we would like to find the speed. So we know that the speed of light, it's still V equals D over T. This is where they try to trap you in those light problems. Keep in mind, it's telling us the time it takes for light to go there and back. So light travels 8.63 kilometers there, but keep in mind, it also travels 8.363 kilometers back. So it's going to and from, and we have to account for that. So the actual total distance the light's going to travel in this example, it's going to be 17.26 kilometers. And that's the big thing we got to watch for in the light questions. Now, the other way you could do that is you could use the 8.63 kilometers, but instead of using 5.51 times 10 to the minus 5 seconds, you could use 2.255 times 10 to the minus 5 seconds. So you could use half of that, because the time it takes to go just from here to here is going to be half of the time it takes to go from the light to the mirror and back. So there's two ways you can approach that, but be mindful of that. So we got that 17.26 kilometers, or if we want to put that in meters, we got this 1.726 times 10 to the 4 meters. So we're going to have this distance the light travels, and we know it's going to do that in a very small time of 5.51 times 10 to the minus 5 seconds. So let's have a look. What is Fizeau going to get? So what we're going to get for this is we're going to get about 3.13 times 10 to the 8 meters per second. So, like I said, these questions, we're not explicitly asking these to test you on Fizeau's method. We're just more getting you to recognize that when you're doing these light calculations, you got to take into account that the light travels from the source to where it's reflecting from and back. So the next one we're going to talk about is we're going to talk about Michelson, but we're going to keep a separate video for him just because Michelson's experiment's actually really important. So stay tuned for that.